students. I welcome you everyone for today's session. So today we will be going to discuss about the chapter waves in physics. So here I will be covering the very important topics and synopsis that we will use in this chapter, waves. So actually we will be going with, so in this session we will be covering, so what is a wave motion, and second, vibration in strings, and third, beats, and fourth one it is echo, and fifth here we will be discussing about the Doppler effect, and then the velocity of sound. The velocity of sound. So, and the next, vibrations of air column. So here in today's session we will be going to cover the wave motion, vibration in strings, beats, echo, Doppler effect, velocity of sound, and vibrations of air column. And in this wave motion topic we will be covering about the transverse waves, and then the type of, these are nothing but the type of waves, that is longitudinal waves and progressive waves, and next the phase difference, and the energy and power and intensity relations, energy, power and intensity of a wave, like what are the equations of that, we will be discussing that. And next, the vibrations, the type of vibrations, like free vibrations and forced vibrations and resonance vibrations, we will be covering in this. And next, the principle of superposition, and last but not the least, the standing waves, and the standing waves are also called as stationary waves. So in today's session we will be going to cover these topics, like for in wave motion. So in that wave motion, the types of waves, that is transverse waves and longitudinal waves, progression waves, and the next, what would be the equation for the phase difference, and the relations like energy, power and intensity of the wave, and the type of vibrations, that are free vibrations and forced vibrations, and what is the principle of superposition, and standing and stationary waves. And after that, the concepts, after covering these concepts, we'll be moving on to the next, vibration in strings, where the most of the mathematical problems in physics from the chapter waves would be given from vibration in strings and beats, echo, and the most important topic, that is Doppler effect. Based upon the few scenarios and some special cases, the Doppler effect is considered to be the most important topic in chapter waves. And next we'll be covering about the velocity of the sound, and what are the effects of the velocity of the sound depending upon the frequency, pressure, and like that. We'll be considering all that, and we'll be looking at this in today's session. And next, the vibrations of the air column. So without any delay, we'll start our session. The first one is waves. So as we all know that what are waves. So waves, actually these are mainly divided into the two types of waves. We can say that mechanical waves, and next one non-mechanical waves. So what is the main difference? It's nothing but the mechanical waves transport energy from one place to another in a medium. That means it requires, definitely if it is a mechanical wave, then the wave propagates through a medium. But then coming to the non-mechanical waves, it doesn't require a medium. It doesn't require, no medium is required for this. So example for this non-mechanical waves are nothing but electromagnetic waves. So what comes under this electromagnetic waves? Nothing but the X-rays and gamma rays, and gamma rays are also called as microwaves. So these waves doesn't require a medium, so this comes under non-mechanical waves. and the mechanical waves that transports the energy from one place to another using a medium. So simply we can say that a wave that requires a medium are classified as mechanical waves. A wave that no longer requires a medium is said to be a non-mechanical waves. And next, we all are familiar with the range of audio frequency range. So actually this could be asked as a bit question, MCQ question. So audio frequency range is nothing but 20 kilohertz to 20 kilohertz, 20 kilohertz, and the waves that are less than, the waves whose frequency range is less than 20 hertz are said to be infrasonics. So infrasonics are nothing but the waves whose frequency range is below 20 hertz are said to be infrasonics. And next, the waves whose frequency are greater than 20 kilohertz are said to be ultrasonics. So this could be asked as a bit question. And the general audio frequency is 20 kilohertz, that ranges from 20 hertz to 20 kilohertz. And next, moving on to, so we know that the waves are mainly classified into transverse waves, and second one, longitudinal waves. So now we will be looking at what are these transverse waves and what are these longitudinal waves and how these two are differed. So first one, it's a transverse wave. So transverse wave. So the particles of the medium. So the particles of medium vibrate perpendicular to direction of propagation of the wave. Are said to be transverse wave. So when particles of the medium that vibrates perpendicular to the direction of the propagation wave, that is said to be a transverse wave. And the general representation of this transverse wave would be, so y is equals to a sine omega t plus or minus kx, or x is equals to, this could be also a sine omega t plus or minus ky, and z is equals to a sine omega t plus or minus ky. So this could be anything. This could be, these variables could be x and y. We can alternate this with x, y, z, or that could be a, b, c. So with these variables, so general representation of the transverse wave is y is equals to a sine omega t plus or minus kx, or x is equals to a sine omega t plus or minus ky, or z is equals to a sine omega t plus or minus ky. So what is it? This is a transverse wave. And moving on to the longitudinal wave. So what is a longitudinal wave? A longitudinal wave is nothing but the particles of the medium vibrate parallel to the direction of propagation of the wave. Propagation of wave is said to be a longitudinal wave. So what was the transverse wave definition? The particles of the medium that vibrates perpendicular. So if the particles of the medium vibrate perpendicular, then it is said to be a transverse wave. And here it is the particles in this medium vibrate parallel to the direction of the propagation of the wave. So then that is the main difference. Here in transverse wave, that was perpendicular and it is parallel here. So that was the main difference. and the general representation of this longitudinal wave and the general wave equation. Simply we can say representation of wave equation, that is x is equals to a sine omega t plus or minus kx. So this is the general wave equation for this longitudinal waves. So example for this longitudinal waves could be the sound waves in gases. So the sound waves in gases are nothing but the longitudinal waves that vibrates parallel to the propagation of the wave. So now we'll discuss about this progression wave. The third one is a progressive wave. So what is this progressive wave? A wave that transfers the energy, a wave that transfers the energy from a point into an infinite medium and never returns to its origin. And never returns to its origin is said to be a progressive wave. So when we propagate a wave through a medium and the medium is an infinite medium, and whatever the wave that we are making pass through this infinite medium, that never returns to the origin, so that such type of waves are said to be the progressive waves. And here uh, the distance traveled by the wave in 1 second is known as wave velocity. So here the wave velocity equation could be defined as wave velocity v is equals to lambda divided by t. This could be also n lambda. So this is the wave velocity, where lambda is the angular velocity and t is the propagation constant. And with this we can define this wave velocity. And when a wave, so we'll consider here when a wave passes from one medium to another medium. So when wave passes from one medium to another medium, then its frequency does not change. So this is the important point that we have to note down. v1 by v2 is equals to lambda 1 by lambda 2. So with this relation we can actually solve a few problems that would be given. So this is about the progression wave. Now we will be looking at the phase difference. So in problems that would be asked, like giving some kind of some relations, and they will ask us to find out what's the phase difference. So we'll be looking at the rough definition. So phase difference is nothing but the difference. So the difference in phases of two particles of a medium, at same instant. Or the difference in phases of a single particle at a different instance is said to be a phase difference. So that's the rough definition. And so the phase difference delta phi is equals to 2 pi by lambda into delta x, where delta x is nothing but the path difference. Well, delta x is nothing but the path difference. Like will be in the questions, it would be given like a particle that is moving from position x1 to x2. So that is nothing but x2 minus x1 or x1 minus x2. That gives the path difference. So here the phase difference is defined as delta x is equals to 2 pi by delta x. This is the most important formula that would be covering in few problems. And next we'll be looking at the energy of the wave. So the energy of a wave. So in this energy of the wave, we will be looking at the average kinetic energy and the average potential energy densities. Average kinetic energy, that is defined as 1 by 4 rho of 2 pi an by lambda whole square. So upon simple calculation, that could be pi square into rho into a square into n square. So this is the average kinetic energy density. And next, the average potential energy density is 1 by 4 rho of 2 pi an by lambda whole square, that is pi square into a square into n square. So we can observe that both are same. So the kinetic energy of the wave per unit volume is given by kinetic energy and its maximum value to the energy per unit volume. So we can observe that kinetic energy maximum to potential energy maximum is nothing but the energy density, that is 2 pi square n square a square and rho. So this is the energy density of a wave. And now we'll be looking at the power of the wave. The power of the wave, and here the power is defined as we know that delta is nothing but the energy density is 1 by 2 rho omega square a square s into dx, where s is nothing but the area. And next, the power P is equals to delta E divided by delta T, that is 1 by 2 rho omega square a square into V into S, where V is nothing but dx by dt. That defines the speed. So this is the power of the wave. So now we will be looking at the intensity. Now we will be looking at the intensity of the wave. So intensity of the wave is defined as I is equals to power divided by area. So that is nothing but 1 by 2 rho into V into omega square into a square. So that gives you 2 pi square n square a square and rho, where rho is nothing but the density. We know that rho is nothing but the density and V is nothing but the speed, and n is equals to frequency. So that is the intensity of the wave. So intensity of the sound wave, that differs. Intensity of the sound wave, that is defined as I is equals to energy density, that is multiplied with the velocity of the wave. So that is nothing but I is equals to 2 pi square rho into a square into n square into v, where a is nothing but, you might confuse a as amplitude or acceleration. A is nothing but the amplitude. A is the amplitude here, and n is the frequency, and rho is the density. Rho is the density of the medium. So this is the intensity of the sound wave. So when intensity of the sound wave that is propagated in a medium, that would be intensity of sound wave propagated in a medium, So that is defined as, that is directly proportional to the a square, that is nothing but the amplitude, that is directly proportional to the frequency square. So with this relation, we can actually get the intensity. And next, moving on to the next, the free vibrations, the type of the vibrations. that is free vibrations and the forced vibrations. Free vibrations and forced vibrations. So these are the two types of vibrations that we will observe. So free vibrations are defined as a body when it is set into vibration and left free. That means the natural vibrations could be observed here. The natural vibrations could be observed here. So example for this, the vibrations in a tuning fork. So the vibrations in a tuning fork are said to be the example for free vibrations, where natural vibrations could be observed here. And the forced vibrations are nothing but when a body is made to vibrate. If a body is made to vibrate under influence of an under the influence of an external periodic force, that means no natural vibrations occurring here, by applying a certain kind of external force, so we are observing these vibrations. So such type of vibrations are said to be the forced type of vibrations. And next, so this is about the difference between the free vibrations and the forced vibrations. And next we will be covering the principle of superposition. Principle of superposition. So principle of superposition is defined as if two or more waves that arrives continuously, the particles of the medium are subjected to two or more displacements and a new wave is produced. And this phenomena is said to be a superposition, principle of the superposition. Like if two or more waves arrives continuously, arrives at the same time, the particles of the medium are subjected to two or more displacements, and with this a new wave would be produced, and that is said to be the principle of the superposition. And that is generally represented as, so when in vector sums, when y is equals to y1 plus y2 plus y3 plus 1, that is nothing but the individual sum of the waves that are added together is said to be principle of the superposition. And the phenomena of the interface and stationary waves and beats are due to principle of, so the phenomena, like we'll observing the stationary waves, and beats, that are, this is nothing but because of the superposition principle. Because of this superposition principle, so these said to be an example, the stationary waves and beats, and these are the examples for this. And next we will be moving to the stationary waves or standing waves. Stationary waves or standing waves. So when two identical waves that are traveling along the same straight line with same speed but in opposite direction are said to be are superimposed, and the result is a stationary wave. Like when wave 1 is traveling in one direction and wave 2 is traveling in another direction, and together with same speed along the same straight line but in opposite direction. So when these two are superimposed, when these two waves are superimposed, that gives rise to the a resultant wave, that is nothing but a stationary wave. So when two identical waves are traveling along this same straight line, with same speed, but in opposite direction, that are superimposed, the resultant wave is a stationary wave or a standing wave. So here will be, when the stationary wave will be considering two cases, when the wave reflected at free end, when the wave reflected from the free end and wave reflected from a rigid end. So with these two cases, we'll be looking at the equations for the standing wave. So the first case, when wave reflected from free end. So here the equations, when two waves, here we are considering two waves. So y1 is equals to a sine omega t minus kx. That is, this is traveling along the positive x-axis. Y2 is equals to a sine omega t plus kx, because these two waves are traveling in opposite direction. That is, so this wave is traveling along the negative x-axis. So the resultant wave is nothing but y is equals to y1 plus y2 according to the superposition principle. So the resultant would be a into sine of omega t minus kx plus a into sine of omega t plus kx. So this gives us, when by taking out of common a, so we'll be getting a of omega t minus kx plus sine of omega t plus kx. So now applying the formula sine a plus sine b, so we'll be getting 2 cos a sine b. So 2 cos a plus b sine a minus b, so that we'll be getting the resultant 2a cos kx into sine omega t. So this is said to be a standing wave. When it is reflected from the free end. And now next we'll be considering wave reflected from the rigid end. So at this case, so the equation would be the sine 2 pi by lambda of x is equals to plus or minus 1, or 2 pi by lambda of x is equals to 2n plus 1 pi by 2. So where n could be 0, 1, 2 and so on, etc. So this is the equation of the wave, that is when it is reflected from the rigid boundary. So we'll be having some properties of this stationary wave. Properties of stationary wave. So we'll be discussing the few important ones, like certain points in mediums situated at equal distances are always in position of rest. So these points are said to be nodes. So nodes are nothing but the points in medium that are situated at equal distances are always in state rest. So that are said to be nodes. And Antinodes nothing but the pressure and density at maximum at nodes. If stationary waves are longitudinal, the displacement of the points. So antinodes are nothing but, so we'll be looking at the definition of the antinodes. Antinodes are nothing but displacement of points in between the nodes. Points in between the nodes is always maximum. So next, the distance between the consecutive nodes. So the distance between the two consecutive nodes. Is lambda by 2. So when distance, this is the two consecutive nodes or the antinodes, two consecutive nodes or antinodes. So when both nodes are antinodes or nodes, so then the distance is lambda by 2. So if we want the distance between the node and antinode, between node and antinode, so that would be lambda divided by 4. So it is one of the important property of this standing wave. And moving on to the next point. So energy density. So energy density is twice that of a progression wave. Twice that of a progressive wave. And next, there is no transfer of energy across any section. There would be no energy transformation. So transferring of this energy doesn't take place here. And next, all particles possess maximum kinetic energy when they are passing through the mean position. So when particles passing through mean position, they will have they will have maximum kinetic energy. So when the particles, they are passing through the extreme position of the when the particles are at extreme position, they will have the potential energy maximum. So these are the few important properties of this standard wave. Now we will be looking at the velocity of the transverse waves. So vibrations of strings. So from this topic, the main mathematical models would be the main mathematical formulas that will be coming across in the problems discussed here. So in this first one, we will be discussing about the velocity of transverse wave. So velocity of the transverse wave, this could be under some cases, like first one, when velocity of the transverse wave propagating along a string. So velocity of the transverse wave along a string is given as under root of T divided by M, where T is the tension and M is the linear density, where T is the tension and M is the linear density. And if mass m0 is considered, if mass m0 is given in the problem, then velocity will be defined as T into L divided by m0, where L is nothing but the length. So this is the case when velocity of the transverse wave, that is along the string. So if it is next case, the velocity of the transverse wave propagating along a string depends upon only on the characteristics of the string. So it is independent of the frequency of propagating wave. So here it is covered that the velocity would be independent of the frequency if and only if when string depends on the characteristics of the string. So next, v is equals to under root of t divided by a into d. That is nothing but root s divided by s d, where s is equals to stress. Stress is defined as t by a. V is equals to under root of t by pi r square d. So where r is nothing but the radius of cross section, And next case is when a metal wire is at T2 degrees centigrade, from when it is between two fixed supports with a temperature T2, and the wire is cooled to T1 degrees centigrade, then the velocity would be v is equals to under root of t by a divided by d. That is nothing but y into alpha, the difference of the temperatures that are mentioned, T2 minus T1, to the d, where y is equals to Young's modulus. We all know this, Young's modulus, and alpha is nothing but the coefficient of linear expansion, and d is nothing but the density. So this is the case. So this would be the velocity when a metal wire that is fixed between the two supports with a temperature T2. So then the wire is cooled at a T1 degree centigrade. Then what would be the velocity? So then that is nothing but under root of y into alpha into T2 minus T1 divided by T. So next case is when a uniform rope of length L and mass m0, that is suspended vertically, like here it is a fixed support, and from it is suspended vertically. So this is the mass m0 that is suspended from one end. At the other end, the mass m is attached. So to this, a mass m is attached. So then the velocity is said to be v is equals to under root of the mass that is attached below into g divided by m. So the velocity at point of suspension. So the velocity at point of suspension would be v2 is equals to under root of the mass that is attached below into g divided by m. So with this difference, v1 by v2 is equals to lambda 1 by lambda 2. That's nothing but under root of m divided by capital M plus small m0. So from this case, so velocity v2 is greater than v1 and lambda 2 is greater than lambda 1. So this is a case when a uniform rope of length L. So this is of length L. So when a rope is suspended vertically from one end, connecting that is to a mass m below. And next case, a uniform rope of length L and mass m0 is hanging on its own weight. Then velocity is said to be v is equals to under root of y into g. So from this, acceleration could be, acceleration is equals to v square minus u square divided by 2s. On substituting this, Lg minus 0 divided by 2L, that is g by 2. So from this time is T is equals to 2 into under root of L divided by g. So this is the case when a uniform rope of length L and mass m0 is hanging on its own weight. So then the velocity is nothing but v is equals to under root of y into g. So then the extension in a string obeying Hooke's law is x1 when the sound speed of sound in is v1. So then we will be discussing the law of tension and law of length and law of mass. So these are the cases. So the law of tension. The law of tension. So the law of tension is nothing but the fundamental frequency of a stretched string is directly proportional to the square root of the tension in the string. So the fundamental frequency of a stretched string is directly proportional to the square root of tension in the string. So that is n is directly proportional to the square root of the T, tension T. And next, a wire of uniform cross section is stretched between 2 points when it is stretched between 2 points and wire is fixed at when one end of the wire is fixed with a load M that is hung. So in that case the velocity would be v1 divided by v2. Considering the densities of that, the velocity would be this. And next, the law of length. So the law of length is nothing but when the fundamental frequency of the stretched string is inversely proportional to the length of the string. So when fundamental frequency n, that is inversely proportional to the length of the string, so that is said to be a law of length. And the law of mass. So the law of mass is nothing but when the fundamental frequency stretched under constant tension and the length n is inversely proportional to the square root of when fundamental frequency is inversely proportional to the m is nothing but the mass. So that is said to be the law of mass. And a few special cases over here. Few special cases like if two different strings vibrate with the same frequency. If two different strings vibrate with same frequency, then we'll be getting n is nothing but the frequency n divided by 2L1 into T1 divided by pi R1 square into D1 is equals to N2 divided by n is equals to N1 divided by 2L1 under root of T1 pi R1 square into D1 is equals to N2 divided by 2L2 under root of 2 pi R2 square into D2. So this is the case when two different strings vibrate with the same frequency. And next we will be discussing the percentage change in the frequency. The percentage change in the frequency. The percentage change in the frequency. So here the first one, when there is a change in tension. When there is a change in tension, then the frequency would be the percentage change into 100 is equals to 1 by 2 into delta T by T into 100. So this is the case when there is a change in the tension. So when there is a change in linear density, when there is a change in linear density, delta n divided by n into 100, frequency change is equals to the minus 1 by 2 into delta m divided by m into 100. So this is the case when there is a change in the linear density. And next one, if there is a change in length, then the frequency change delta n into n 100 is equals to the delta L minus delta L divided by L into 100. So this is the case when there is a change in length, and when there is a change observed in the radius. So when there is a change in radius, so then the frequency change is delta n into 100 is equals to minus delta r into r. So we are observing a common case, like if there is a change in tension, so then with this that would be delta T by T, and if there is a change in linear density, that is considered as delta m by m, and if there is a change in length, the length with this change is considered, and if there is a change in radius, and the radius is considered, and if there is a change in density, so then the frequency change would be minus 1 by 2 into delta of rho divided by rho into 100. So this is the cases. So now we will be discussing about the sonometer. So what is a sonometer? Sonometer is nothing but it's a rectangular hollow wooden box that having the holes. So a rectangular hollow box that having holes. So here what type of vibrations could be observed? So free, as it is free vibrations over that could be observed. So it is a hollow rectangular wooden box with holes. In this, free vibrations are observed. So here in this sonometer will have first law as, so if NL is equals to constant, so by changing the tuning forks and noting the corresponding vibrating lengths, the tension T and the linear density M are constant. And the second law, so root T by L should be shown as constant. So if NL is shown as constant, so then it is the first law, by keeping this tension and the linear density as constants, and under root of T divided by L is shown as constant. And third law, in which L into under root of M is shown as constant. And next we will be discussing about beats. So what are beats? So beats are nothing but when two progressive sound waves of nearly equal frequencies, of equal frequencies n1 and n2 that are nearly approximately equal, So if these two progressive waves interfere, so then beats are produced. So when two progressive waves of equal frequencies N1 and N2 that are interfered, then beats are produced. So with this we'll be having some few cases like the angular velocity. So what would be the angular velocity? Angular velocity of the combined wave when these two progressive sound waves that are interfered, so then beats are produced. So then the beats for this resulting one, so the angular velocity would be omega 1 plus omega 2 divided by 2, or frequency would be n1 plus n2 divided by 2. So then amplitude is not constant for these beats, and but it changes with the time, and the beat frequency. So the beat frequency is n1 minus n2, nothing but the frequencies of the first one, and that we are considered that those two are nearly equal frequencies. So the difference of that gives us the beat frequency, and the ratio of maximum to minimum intensity. The ratio of maximum to minimum intensity is defined as I1 divided by I2 is equals to A1 plus A2 whole square divided by A1 minus A2 whole square. So this is where A is nothing but the amplitude. So this is the intensity when intensity of the first one with that is maximum, and this is the minimum. So this gives us A1 plus A2 whole square divided by A1 minus A2 whole square. And next we will be looking at the tuning fork. So tuning fork, it's nothing but produces a pure tone when excited gently. So sound having a single frequency, what is actually we'll be looking at what is the definition of the tone. So a tone is nothing but a sound having single frequency. A sound having single frequency is said to be as a tone. So a tuning fork is nothing but which produces pure tone when it is excited, so then that is said to be a tuning fork. So the frequency of the fork is directly proportional to the speed. So here the frequency of the tuning fork is directly proportional to the speed of the sound. So that is defined as n is directly proportional to t divided by L square into y by d. So when to determine the frequency, to determine the unknown frequency, of a tuning fork, we have some special cases here. So the first one, if two sound waves of wavelength lambda 1 and lambda 2, if lambda 1 and lambda 2 are said to be the two sound waves that produces produces delta n beats per second. Then the velocity is given as v is equals to lambda 1 lambda 2 delta n divided by lambda 2 minus lambda 1. So this is the case when two sound waves are considered with the lambda 1 and lambda 2 are considered. And next, if same tuning fork produces same beat frequency with two stretched strings L1 and L2, if same tuning fork produces same beat frequency delta n with two stretched strings of length L1 and L2 is given as delta n is equals to n1 minus n, that is equals to n minus n2. So the ratio could be considered n1 minus n2 is equals to L2 divided by L1, or could be considered as the difference of delta n minus delta n is equals to L2 divided by L1. So with these few cases, the tuning fork of an unknown frequency could be determined. So coming to the next one is nothing but the Doppler effect. So Doppler effect, we can consider this Doppler effect, the most problems, the mathematical problems could be considered from this here. So Doppler problems, there are a few formula over here. So if a source approaches a stationary observer, apparent wavelength is, so it is there are some cases. So what is actually Doppler effect means? The apparent change in frequency due to the relative motion between the observer. So if there is a change in frequency between the observer and the source, then that is said to be a Doppler effect. So if there is a change in frequency, due to the motion between the observer and the source, is said to be a Doppler effect. So we'll be having some cases like when source is stationary and the observer is approaching or moving behind from the source, and when observer is stationary and the source is coming like when an observer is approaching the source or observer is moving behind the source. So in that cases, we'll be having a few changes with the formula, and with that we'll be calculating the wavelength. So the first case is when source approaches when source approaches a stationary observer. So here it is saying that the source is in motion but the observer, that is stationary. So source is in motion and the observer is at a rest position, that means a stationary position. So in that case, the wavelength lambda dash could be v minus vs divided by n. So that is nothing but v minus vs divided by v into lambda. So where vs is nothing but the velocity over the source, and v is the velocity of the observer. We can write this as v naught also. So v naught minus vs by v naught. So lambda is nothing but the velocity. So v is, so here this could be shortened as delta lambda is equals to vs divided by v into lambda. So this is the case when source is in motion and observer is at rest position. And what if then second case is when source moves away from the stationary observer. So that means the observer is the observer is at a rest position, like he or she is in a rest position, then the source moves away from them. Then what was the previous case? The stationary observer, when the source approaches him, that means moving towards the observer. So in that case we got this as v minus vs divided by v. So here he is approaching, so then the lambda dash is equals to v plus vs divided by n, that is equals to v plus vs divided by v into lambda. So this could be the wavelength is increased, that means then lambda dash is equals to vs by v into lambda. So next case, so if observer moves towards a stationary source and he receives additional number of waves, like if the observer, so till now we saw that the source is approaching the stationary observer. So in this case we will be seeing observer moves towards the stationary source. Stationary. So stationary is nothing but the source is at a ideal the source is at a rest position. So in that case, the frequency is considered as v plus v naught divided by v into n, that is nothing but 1 plus v naught divided by v into n. So this is the case when the observer is in motion and the stationary and source is at a rest position. And next case, if the observer moves away, from the stationary source, so then the frequency would be v minus v naught divided by v into n, that is nothing but 1 minus v naught divided by 1 minus v naught divided by v into n. So when it is moving away from the source. So what if those two are, till now we have seen one, either source or observer are at stationary position and observer or source are moving away or approaching. So in that case we have shown the 4 cases. Now what if the source and the observer are both in motion? So if they both are in motion, then what would be the frequency? Then apparent frequency is said to be v plus or minus v naught divided by v plus or minus vs into n. So if he or she is approaching, if approaching we'll use this plus symbol. If he is moving far away, moves away from that either one of them, so we'll be using this minus symbol. So if he is approaching, so v plus v naught divided by v plus vs, where v naught is nothing but the velocity of the observer and vs is nothing but the velocity of the source. And if he or she is approaching, he is moving away, then it is defined as v minus v naught plus v minus v naught divided by v minus vs. So if he moves away from the, if both are in motion and moves away, then it is said to be this one. And next, if medium between the, so here the next point, so if source, observer and the medium in them, and the medium over that is also in motion. So if these 3 cases are in constant or in motion, then the frequency would be v plus or minus wind velocity. Here w is nothing but the wind velocity, and v plus or minus w plus vs into n. So this is the case when the source, observer and medium are in motion. So if they are moving in the both same direction, if wind blows along the same direction, so then we'll be considering v plus w. So if they are in opposite direction, so then we'll be considering v minus w. So these are the 6 important cases in this Doppler effect. And next, velocity of a sound in a medium. Velocity of a sound in medium. So velocity of sound in a medium. So velocity of a sound in a medium is defined as E divided by T, where E is nothing but the modulus of elasticity and D is nothing but the density. So here the velocity of the sound in a medium. So velocity in solids would be maximum. So the velocity of the sound would be maximum in solids. So that would be minimum in gases. So the velocity, so if we consider, for example, velocity of the steel and velocity of the water and velocity of the air. So obviously the velocity of the steel, that is a solid, here this will be having the highest velocity, and the minimum velocity would be velocity of the air, as we know that velocity of the air. So in gases the velocity of the sound would be minimum. And next, so velocity of the sound in gases, we have Newton's formula. So Newton's formula. So in this Newton's formula, so the velocity of the air is equals to the under root of rho divided by d. So rho divided by d. So this is the Newton's formula for the velocity of sound in gases. And the Laplace correction, so this value would be, as rho is a constant, so 1.01 into 10 to the power of 5 divided by 1.3. This gives you 297 meters per second. This is the constant value, and this is an isothermal process. And next, the Laplace correction. So the Laplace correction formula, by assuming the sound transmission through gases, is an adiabatic process. So the bulk modulus of elasticity. So here the bulk Laplace correction. So the Laplace correction. So Laplace correction, Newton's formula. So here what it's an assuming this as an adiabatic process. So we will be getting the velocity as v is equals to under root of gamma into rho divided by d. So as of these constants, we know this under root of rho divided by d from Newton's formula as 279. So this gives you 331.3 meters per second. So this is about the velocity of the sound in gases. Now we will be considering the factors affecting the velocity of the sound. Velocity of sound. So when the velocity of the sound, when there is a change in density or pressure or temperature, so with that kind of cases, so the velocity will be increasing or decreasing. We will be looking at those. So the first case is effect of density. So when there is increase or decrease in the density, so then how it affects the velocity of the sound, we'll be looking at that. So here the velocity is inversely proportional to the square root of 1 by d. So here we can see that it is inversely proportional. Like if velocity increases, then definitely the density is going to decrease. If velocity is decreasing, then density is increasing. So with that relation we can write v1 is inversely proportional to 1 square root of 1 by d, that is V1 divided by V2 is square root of D2 divided by D1. So this is the case. So, and next, effect of pressure. An effect of pressure. So here, at constant temperature, the velocity of the sound is independent of change of pressure. So if we have a constant temperature, then definitely there is no change is observed over the velocity of the sound, because pressure, if there is a constant pressure, it is independent of pressure. It is independent of the pressure. And next, effect of the temperature on the velocity. Effect of temperature on velocity of sound. So what if the temperature is changed? So it's nothing but, so we know that velocity is directly proportional to the temperature, because from the equation V is equals to under root of gamma into rho divided by d. That is from the Laplace correction. From this Laplace correction, we can change this to under root of rho into P into V divided by M. This density could be written as M divided by V. So from here, P is nothing but nRT. So we know that PV is equals to nRT. So from that, substituting PV is nRT into this M. So from here, we can say that V is directly proportional to the square root of T. So from that, we'll be getting the effect of the temperature. Like if temperature is increased, then definitely the velocity of the sound is also going to increase. So V2 divided by V1 is equals to under root of square root of T2 divided by T1. This is the effect of the temperature. So effect of the wind velocity. So effect of wind velocity. So effect of the wind velocity. So from the equation above considered, like V is equals to under root of gamma into rho divided by d. So in the previous we have substituted R into this density as P into V by M, and PV is substituted with gamma into MRT divided by M into M. So PV is equals to nRT was substituted, and from that we can get RT into under root of M1 gamma 1 divided by M1 plus M2 gamma 2 divided by M2 plus M3 gamma 3 divided by M3, where M1, M2, small m1, M2 are nothing but the masses of the gases. And now we'll be looking at the displacement of pressure waves. Displacement of pressure waves. Displacement of pressure waves. So in these cases, so sound wave may be described either in terms of the displacement or the pressure. So by considering displacement or the pressure, a sound wave would be described. So here will be, if we consider the displacement as y is equals to a into sine omega t minus kx, if we consider this as a displacement, and next the pressure as P is equals to minus B into dy by dx. By differentiating this displacement equation, we will be getting dy by dx as minus k into a into cos of omega t minus kx. By substituting this here in pressure, P is equals to minus, we will be getting minus into minus plus, that is a into b into k into cos of omega t minus kx. So considering this as p naught, we will be considering that as a p naught as a constant cos of omega t minus kx. So this is, so when sound of the wave could be described either in terms of the displacement or the pressure. So by considering the displacement and the pressure equations, we got this pressure equation as P is equals to P naught into cos of omega t minus kx. And next, the vibrations in the air column. So the vibrations in air column. So here the vibrations in the air column that could be observed in two cases, like when it is a closed pipe and when it is open pipe. So in these two, we could observe the variations. So in a closed pipe, so the one end would be closed. The one end would be closed when the wave, like this, when the wave. For example, if we consider a single wave, so then the length is nothing but L is equals to lambda by 4. So the relation between the length and the lambda is lambda is equals to 4L. So from here the fundamental frequency for the first harmonic. So we can consider this as the first harmonic. So then the fundamental frequency N is given as V by lambda. As we know that we got lambda value as 4, then V divided by 4L. So in the next mode we will be getting, so in this is for the first harmonic, and for the second harmonic we will be getting L is as 3 lambda 1 by 4. So from here we will be getting lambda 1 is equals to 4L divided by 3. From here the next frequency N1 is equals to 3V by 4L, that is nothing but 3N. So by considering this harmonics, first harmonic and second harmonic, the ratio of the frequencies would be 1 is to 3 is to 5 is to 7 and so on. So the odd number ratios could be observed in this closed pipe. So when during this open pipe, when the two ends are open, so if we consider here the vibrations for the first harmonic would be the vibrations for the first harmonic. So for the first, the length would be L is equals to lambda by 2. So with that frequency N is equals to V by lambda, that gives you V by 2L. So this would be the first harmonic, and considering the second harmonic, we'll be getting N1 as V by lambda 1 as 2 times of V1 by 2L, that is nothing but the 2N. So here the ratios of the frequency would be 1 is to 2 is to 3 is to 4 is to 5. So here, so during this closed pipe, the first harmonic and the second harmonic, the frequency ratios would be the odd numbers, like 1 is to 3 is to 5 is to 7, and here it is 1 is to 2 is to 3 is to 4 is to 5. So this is about the vibrations in air column, in closed pipe and in an open pipe. And next we'll be covering about the characteristics of the musical sound. Characteristics of musical sound. So here we will be discussing the few characteristics. So pitch. So the pitch is characteristic. So pitch is considered as the characteristic of the musical sound that distinguishes between a sharp sound and a. So the pitch here, it actually considered as a characteristic because it tells us the difference, what is difference between the sharp and the dull sound. And next, the pitch of a sound is directly proportional to the frequency and is inversely proportional to the intensity. And next, the pitch of a roaring lion is less than So if we consider the pitch between the roaring of a lion and the mosquito's noise, obviously we can't say that the roaring of the lion pitch would be more. The roaring of the lion have a less pitch when compared to the mosquito's noise. And next, the pitch of a girl or a child is always greater than the pitch of an adult. And next, the relation between the loudness and the intensity is defined as, so the relation between the loudness L and intensity I is defined as L is equals to K into log E into I, or L is equals to log of I divided by I naught. So this is the relation between the loudness and the intensity, where K is the proportionality constant, and I naught is the threshold frequency. So these are the few main important concepts through which we'll be having most of the problems. So most of the problems would be coming from the mathematical problems, expected to be most from the Doppler effect, and next the vibration, and next the vibrations of the air column, and next the velocity of the sound. So here we have covered the open pipe and the closed pipe, and based on this first harmonics and second harmonics will be having the most of the problems. And Doppler effect, when source and the observer, what if the source is stationary and observer is moving away or approaching, or observer is at stationary position and source is approaching or moving far away, and when source and observer both are in motion, when source, observer and the medium is also in motion, so with that cases what would be the velocity and the velocity of the sound. So the most of the mathematical problems would be covered from these three main topics, and at the same time from beats, and the theory part and the theoretical MCQs would be mostly asked from the transverse waves, longitudinal waves, and the progressive waves, and what from the phase difference, and superposition principle. So most of the theory questions would be asked from here, and at the same time energy, power and intensity. So the most of the expected theory questions are from these topics. And from here the mathematical problems are mostly covered. I hope you guys found this session informative.